Picture this. A piece of critical financial software passes every single one of its unit tests. It gets the green light, gets deployed into production, and then it still reports disastrously wrong data to federal regulators. Yeah, it is literally a multi-million-dollar nightmare. Welcome to This Explainer. Today we're unpacking an incredibly fascinating document. We're looking at an award-winning test catalog from the Anthropic Claude Code Hackathon that specifically exposes the subtle, hidden flaws in complex financial logic. We are going to explore the dark art of breaking software on purpose and uncover why thinking like an adversary is absolutely the only way to build truly resilient systems.
So, we've got to start with this core question. Honestly, normal happy path testing is kind of the naive victim in our detective story. Happy path testing is when a developer feeds the system perfectly clean, completely expected data, just to see if the main features function. But let's be real. High-stakes financial engineering isn't a perfect world. It's chaotic. It's unpredictable. Just checking if the system works under ideal conditions is a recipe for absolute disaster. We need a completely different mindset. While normal testing tries to prove that the code does what it was built to do, we need to prove what happens when everything goes completely, catastrophically wrong. And that's where adversarial testing comes in. Instead of just checking if normal inputs work, adversarial testing plays the cunning detective. It actively hunts down those subtle edge cases, the data contradictions, and the weird rule overlaps that could cause devastating financial consequences. You aren't just writing basic tests here. You are essentially leaving brilliant, glowing warning signs for the exact scenarios under which a future developer, or maybe a bad data pipeline, could accidentally introduce a critical bug. It's all about anticipating the failure before it even has a chance to happen. Okay, let's lay out our actual crime scene. The system we're testing is called a default rate semantic engine. Now, its job sounds super simple, right? Just decide which loans in a massive portfolio are considered defaulted. But here is the major catch. In a real bank, different departments operate in deep silos, and they have completely colliding definitions of what makes a loan defaulted. The canonical standard says a loan is defaulted at 90 days past due. Easy enough. But the risk team, they are extremely cautious, so they want to see loans flagged at just 30 days past due. Meanwhile, the finance team is over there subtracting recoveries, the board forces all restructured loans to be counted at 60 days, and regulatory requires strict origination cohort filters. This insane web of overlapping roles is exactly the kind of dark corner where bugs absolutely love to hide. So, here is our roadmap for hunting down these bugs. First up, the setup. Why normal testing fails. Next, the silent assassins, boundaries and decimals. Then, rule contradictions, state machines. After that, system-level chaos, data ghosts and clones. Then we hit the climax, fuzzing and property testing. And finally, building bulletproof systems.
Section 1. The setup. Why normal testing fails. Let's set the stage with the 15 adversarial PyTest cases that actually won the Anthropic Hackathon out of over 1,500 participants. The really crucial point to understand here is that this catalog doesn't just test basic features. It deploys 15 highly targeted traps spread perfectly across 6 incredibly complex categories. And these aren't just random guesses. From threshold boundaries to monetary precision and from referential integrity to concurrency, every single category is meticulously designed to exploit a specific vulnerability in financial logic. They're engineered to catch a devious bug way before it ever has a chance to quietly ruin a production dashboard. We're going to walk through the most fascinating examples from these categories right now. Section 2. The silent assassins. Boundaries and decimals. Let's meet our very first villains. Off by one threshold errors and floating point rounding traps. Now, adversarial boundary testing is just incredibly devious. Let's think about it. In the canonical rules, a default triggers at exactly 90 days past due. The boundary day itself counts. Our test checks 89, 90, and 91 simultaneously. Why do we need to check the exact boundaries so intensely? Well, imagine a reviewer looks at the code, sees greater than or equal to 90, and decides to fix it to just greater than 90 because, they think it reads a little cleaner. That single, tiny, seemingly innocent edit silently exempts every single 90-day loan from the default calculation. And since 90 is usually the most common default value in a real portfolio, that tiny human error instantly corrupts the entire dataset. The adversarial test perfectly anticipates this exact mistake. Next up, we have to compare Python's exact decimal type against what I like to call insidious float contamination. In normal computer math using standard floats, if you add 0.1 and 0.2, the computer doesn't give you 0.3.
It gives you 0.3000000000004. Now, in a casual mobile app, that microscopic rounding residue doesn't matter at all. But when you're aggregating billions of dollars across a massive loan portfolio, that microscopic float contamination compounds into a massive, very real regulatory misreporting disaster. When we look at how this is actually implemented in the code, this test enforces strict decimal purity. It's built to anticipate future human error, like, say, a future contributor accidentally adding a helper function to serialize data for a JSON API, and they just use a standard floating point conversion because it's quick. Standard happy path tests might let that slide if the numbers look close enough. But this adversarial exact decimal assertion, it catches the float contamination instantly. Without this trap waiting in the dark, that standard float conversion could literally throw off downstream regulatory submissions by a whole basis point. Moving right along to Section 3, Rule Contradictions State Machines. Let's see how these boundary issues stack up into complex state machine contradictions, where business rules violently collide. Think about the life cycle of a single loan. It moves through different states over months, maybe years. A naive test checks a loan's status flags in total isolation, but an adversarial test verifies the exact hierarchy of overlapping rules. For example, if a borrower gets back on track, their loan is restructured, and its days past due drops under 90. The canonical rule says, great, that loan is now cured. However, if that same borrower is currently in bankruptcy proceedings, that legal state absolutely must override the cure. An adversarial test intentionally creates this chaotic scenario, a loan that is simultaneously restructured, under 90 days, and bankrupt. It's actively hunting for the exact bug where a developer might write a cure shortcut in the code that accidentally bypasses the critical bankruptcy check. Section 4, System-Level Chaos, Data Ghosts, and Clones. Now we're escalating from individual loan logic to system-wide referential integrity. This part perfectly illustrates the danger of nothing versus the danger of too much. Take the danger of nothing, for example. What happens if the system processes a completely empty portfolio? A naive system divides by 0 and crashes. Or worse, it returns a silent not a number, known as a NaN. That NaN can silently propagate like a virus through the entire system and wipe out your top-level dashboard KPIs. The adversarial test forces an exact 0 return instead. Now flip that and consider the danger of too much. Here we test for silent clones. We feed the system a portfolio with 2 identical loan IDs. This perfectly anticipates a classic data pipeline bug, a Cartesian product, where a bad database join effectively multiplies rows against each other. It silently inflates the default numbers by double counting a loan without a single person noticing. Section 5, the climax, fuzzing and property testing. Okay, hand-coding a few specific edge cases is great, but what if we took it to the absolute limit? The source catalog uses a really powerful concept called property closure on the reconciliation report. So instead of testing specific hard-coded numbers, it tests the overarching truth of the system itself. The reconciliation report explains exactly why the risk team numbers differ from the canonical numbers. The property closure test proves a mathematical truth. It guarantees that the sum of every single divergence cause perfectly matches the total number of divergent loans, meaning even if you throw 1,000 randomly generated, completely chaotic portfolios at the system, this test absolutely guarantees there will be no missing, no uncategorized, and no double-counted reporting data. It literally mathematically proves the ledger is balanced. And here we see the Hypothesis Python library in action. It fuzzes up to 10,000 different, completely randomized portfolios just to enforce a concept called monotonicity, which is really just a fancy way of saying one number must always go in the same direction relative to another. Think about it. The risk team considers loans defaulted at just 30 days. The canonical model waits until 90 days. Therefore, by the absolute fundamental laws of logic, the risk team's default count must always be greater than or equal to the canonical count. Always. This portfolio-level fuzzing test guarantees that a developer's well-intentioned but naive performance optimization doesn't accidentally drop loans in the pipeline and logically invert the relationship between those two teams. Always. Section 6. Building bulletproof systems. To wrap up our explainer today, let's summarize what all of this adversarial thinking actually means for you. The biggest takeaway here is a complete shift in mindset. Testing isn't just a chore you do to pass code coverage metrics, it's about aggressively, proactively anticipating failure. Every single test we've looked at today documents a concrete, real-world disaster scenario, Whether that's a stale database job, a tiny float trap hiding in JSON serialization, a missing regulatory cohort filter, or a bad database join that creates phantom data. By connecting abstract mathematical invariants to visceral operational consequences, developers can build truly bulletproof systems that actually survive contact with the real world. So, I want to leave you with this final thought for your own engineering projects. Are you just verifying that your code works when the world is perfect? Or are you mathematically proving that it cannot be broken when everything goes completely wrong? Thanks for joining me on this explainer. Catch you next time.